To be able to pass variables to functions without transferring ownership, Rust has a feature called references. References allow us to refer to a value without taking ownership of it. We can change the function signature of our SumFN to accept a reference to a string instead of taking ownership of the string. We do that by adding an ampersand before the type. Now, the function expects a reference. When the s variable gets out of scope, the string will not be dropped because s is not the owner of the string. The function just borrows the string. This is why in Rust we call passing references as parameters borrowing. We have to explicitly pass a reference when we call functions though. So you can see that here the compiler will give us an error because it is expecting a reference to a string, but we are passing a full string. So when we pass a reference, we have to explicitly add the ampersand in the function call also. So just like normal variables, references are immutable by default. So here, if we try to append to our string some value, let's say a, the compiler will actually complain because we cannot borrow it as mutable as it is behind a reference, which is immutable by default. So there is another type of references called mutable references, and we specify them by typing the mute keyword after the ampersand. So now this function is fine and it expects a mutable reference. But again, we can see that the compiler complains about the way we call the function because we also have to explicitly pass a mutable reference when we want to use one. So if we also type the mute keyword here, now everything is happy. If we come to the console to make sure, we can see that our code compiles. Okay, that's great. So there is an important rule for references. In the same scope, we can have as many immutable references as we want, or we can have a single mutable reference. So as many immutable as you want, or a single mutable one. Let's see this in practice. If we create two variables here, let's call them s1, which takes a reference to our input, and s2, which also takes a reference to our input. And then we can just print both of them. And so now we print the one and the other, and we pass s1 and s2. Okay, so now we have two immutable references to the string that's owned by input, and this is completely fine. If we actually come here, we can see that our code builds perfectly fine. So if we change one of these references to be a mutable one, so we convert the s1 to be mutable, suddenly we are no longer able to compile our code because we cannot borrow input as immutable because it is also borrowed as mutable. So it actually tells us exactly where the problem is. So when we try to create the s2 variable with an immutable borrow, we have already mutably borrowed the input for the variable s1. So the compiler will not let us have mutable borrow and an immutable borrow at the same time. So if we have a mutable borrow, we cannot have any other borrows. Like this is also true if we convert the other one to mutable. So if we try to have two mutable borrows, it will still fail in the same way because we can only have a single mutable borrow or as many immutable borrows as we would like. So this restriction allows mutation in a very controlled fashion. Like new people to Rust struggle with this because in most languages, like you can just mutate data whenever you'd like. But there is a great benefit from this. So the benefit of this restriction is that Rust prevents data races at compile time. This is incredibly powerful. Like data races are some of the hardest problems to debug. Just trust me on this one. And When you're writing concurrent code in other languages, you have to always think about data races and how to prevent them. But Rust gives us the superpower of statically guaranteeing that there is no way that we have a data race in our code if it compiles. This is one of the incredible Rust features. To quickly point out how smart the compiler is, here we can turn these mutable references off, so we just have two immutable references, everything is fine, but you can notice that our input is mutable. So we do have a mutable reference, which is the input itself, and we do mutate it down here. But somehow the compiler still lets us have two immutable references and actually use them in the print line. The reason for this is that the compiler is smart enough to figure out that after this point here, where we print them, we do not use any of these references ever again. So it lets us actually use them because it knows that the input will be mutated after we're done with them. So actually, if we move this print line after the call to this function that gets a mutable reference, and we go back to the console, our code will not compile anymore because, again, we have an immutable borrow for the S1 in this case, and then we're trying to create a mutable one and pass it to the function. This just shows how smart the Rust compiler is. Okay, so let's delete this. Now that we know what borrowing is, we can actually get rid of all the extra code that we have and actually see how it would work for our reading from the input. So the readLine function expects a mutable borrow for a string. So it will mutably borrow our string, it will fill it with the input from the console, and then we still regain ownership of the string and we can continue using it with the added data. So we can actually test that by printing the string. So if we just print our input and we pass the input string here. So now if we go to the console and we run our code, it will stop and wait for our input, so we can type 1, 2, 3, and then we see that it actually prints our input as 1, 2, 3. So the readLine function mutably borrows the string, changes its content by, in this case, filling it with the input from the console, and then we can keep using the string.